Hello, my name is Frédéric Meunier and I am a professor in mathematics at École Ponts. I am doing my research at CERMICS, which is the research center in applied mathematics of École Ponts. Did you know that at any moment there is a point on Earth that has exactly the same barometric pressure and the same temperature at the point that is diametrically opposite, the antipodal point? Or did you know that there is always a way to divide a cake between three persons, so that each person thinks his part is as good as each of the two other parts? These results are illustrations of so-called fixed-point theorems. A large part of my activity consists in working on discrete counterparts of such theorems. Discrete means that the objects I'm manipulating are formed by indivisible elements that can be counted. The first result I have stated says that there is always a special point on Earth, such that the point directly opposite on the other side of Earth has the same barometric pressure and same temperature. This is a fixed point theorem from continuous mathematics and not from discrete mathematics. There are so many points on Earth that they cannot be counted. Same thing for the pressure and the temperature. There are so many possible values they cannot be counted. I am trying to understand what kind of statement would be a discrete version of this result. The second result I have stated says that, given a cake and three persons, I can divide the cake into three parts and assign each part to a distinct person so that he is convinced his part is as good as any other part. Same thing here. What if the cake is now a necklace formed by finitely many bits? Is it still possible to achieve such an NV3 division? In other words, what is the discrete version of the cake division result? It turns out that discrete versions of fixed-point theorems are often more versatile and lead us to generalizations. Moreover, discrete versions also open the door to computation questions. What is fascinating with the results I have mentioned is that they ensure the existence of something without saying how to find this thing. In particular, I am trying to understand how difficult it is to find the special points on Earth or the NV3 cake division. This research has no direct application in the concrete world. Anyway, it is in relation with many concepts from economy, sociology or management, and progresses from this research help better understand these concepts and their applications. I am also working on more concrete topics from operation research. Operation research mixes discrete mathematics and computational challenges as well. It aims at designing methods for the optimization of industrial processes in a broad sense. The typical example is the traveling salesman problem. Given points to visit on a map, in which order should I visit them so that my tour is as short as possible? Obviously, methods for this problem will be relevant for logistics or transportations. Currently, I am working on methods for designing the schedules of pilots in airlines. This is very challenging because there are hundreds of pilots, the constraints are numerous, and on top of that, the seniority of the pilots has to be taken into account. To summarize, discrete mathematics are fun, diverse, challenging, and useful.